Chemical analysis. Chemical analysis involves the qualitative and quantitative determination of the chemical composition of materials. It is a fundamental aspect of materials science and engineering, providing critical information about the elemental composition, molecular structure, and chemical properties of substances. Chemical analysis techniques are used in various industries, including pharmaceuticals, environmental monitoring, food and beverage, forensic science, and materials research. Here are some common methods of chemical analysis. 1. Spectroscopic techniques. Atomic absorption spectroscopy, AAS, measures the concentration of specific elements in a sample by analyzing the absorption of light at characteristic wavelengths by the atoms in the sample. Inductively coupled plasma optical emission spectroscopy, ICEPO, ICEP-EOS, quantifies the elemental composition of a sample by analyzing the emission of light from excited atoms in an inductively coupled plasma. Visible spectroscopy determines the concentration of analytes in a sample by measuring the absorption of ultraviolet or visible light. Infrared spectroscopy provides information about the chemical bonding and functional groups present in a sample by measuring the absorption of infrared radiation. Nuclear magnetic resonance spectroscopy, NMSR, analyzes the nuclear spin properties of atoms in a sample to determine molecular structure and chemical environment. Mass spectrometry identifies and quantifies the chemical composition of a sample by analyzing the mass to charge ratio of ionized molecules. 2. Chromatographic techniques. Gas chromatography, GC, separates and analyzes volatile compounds in a sample based on their distribution between a stationary phase and a mobile gas phase. Liquid chromatography, LC, separates and analyzes non-volatile or semi-volatile compounds in a sample based on their affinity for a stationary phase and a mobile liquid phase. High-performance liquid chromatography, a form of liquid chromatography that uses high-pressure pumps to achieve faster separations and higher resolution. Ion chromatography, IC, separates and analyzes ions in a sample based on their charge using ion exchange resins or ions. Selective columns. 3. Electrochemical techniques. Bed potentiometry measures the voltage or potential difference between an indicator electrode and a reference electrode to determine the concentration of ions in a sample. Voltammetry measures the current flowing through an electrochemical cell as a function of the applied potential to analyze redox reactions and quantify analytes. Telemetry quantifies the amount of substance in a sample by measuring the amount of electricity required to carry out a specific chemical reaction. 4. Wet chemical methods. Wet titration determines the concentration of an analyte in a sample by reacting it with a standardized solution of a known concentration. Gravimetric analysis determines the concentration of an analyte in a sample by measuring the mass of a precipitate formed during a chemical reaction. Digestion and extraction involves the dissolution of a sample in an appropriate solvent, followed by separation and quantification of specific compounds or elements. 5. X-ray techniques. X-ray fluorescence determines the elemental composition of a sample by analyzing the characteristic X-ray emission produced when the sample is irradiated with X-rays. Ray diffraction analyzes the crystallographic structure of materials by measuring the diffraction pattern produced when X-rays interact with the sample. Chemical analysis techniques are selected based on factors such as the nature of the sample, the analytes of interest, the required sensitivity and specificity, and the desired analytical throughput. These methods play a crucial role in quality control, research and development, environmental monitoring, and forensic investigations across a wide range of industries.